Morning, Dan.
Good morning.
So today we are interrupting our regularly scheduled Why This Universe postings. If you've been listening to our recent episodes, you're probably expecting String Theory Part 3, which is on the way. But today we're interrupting the flow for a kind of special announcement in response to an announcement that the IceCube experiment put out just this Thursday.
That's right. So IceCube is perhaps the most important neutrino telescope in the world. I would say just the most important neutrino telescope in the world. They've been seeing neutrinos from space for quite a while now, since I think 2013 was their first announcement. But we really haven't known where those neutrinos are coming from. And now we think we know at least where some of them are coming from. And that's pretty exciting. It's from a galaxy in our own kind of cosmic backyard that goes by the name of NGC 1068. And this isn't just any old galaxy. It's a galaxy with a big old black hole doing a lot of like wild stuff in that immediate vicinity around the black hole. So we're going to spend this episode of Why This Universe talking about this discovery, what it might mean, a little bit about the context and history of neutrino astronomy, and what it might teach us about supermassive black holes, cosmic ray acceleration, and the future of neutrino astronomy. This episode of Why This Universe is supported by Wondrium. Wondrium is a mind-blowing subscription service that offers thousands of video and audio courses on a huge range of topics. I've been a big fan and a regular consumer of Wondrium's content for the past 15 years or so, and over that time I've listened to dozens of their courses, including ones on history, philosophy, literature, math, and science. For me, it's kind of like taking an intro-level university course from a great professor on a subject you've always wanted to know more about, but without the big tuition fee, and all in the comfort of your own home or daily commute. I recently started listening to a series in Wondrium on the topic of African American history. Over 12 lectures, this course explores this important piece of American history from the end of slavery through the era of Jim Crow. So if you want to learn some more about African American history or just about anything else, give Wondrium a try. You can sign up for Wondrium now through our special URL to get a month of unlimited access for free. Just go to wondrium.com/universe. That's wondrium.com/universe.
You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper. So just for some context, let's stop for a second and think about the big picture of the human endeavor we call astronomy. Most of that history happened before we had telescopes. And at that time, all of astronomy was just limited to what you could see with your eye, looking up at the sky.
Right, so people tracking with their eye the movement of the moon or the movement of different stars or constellations, painstakingly writing them down on paper,
It would have been a hard time to be an astronomer. But, for most of intellectual history, that's the way it was done. We didn't know how to build a telescope yet. And Galileo didn't invent the telescope, but he was really the one to bring that device to astronomy. And it opened up huge worlds of things you could look at. Stuff you could just not see with your human eye. You could see the moons of Jupiter, at least some of them. You could see the rings of Saturn. You could see phases on Venus. All sorts of stuff you couldn't see before. You could start to resolve stars that before were just kind of part of the blurry Milky Way. It changed astronomy forever. But then, for a few hundred years, we kind of did the same sort of stuff over and over again. We built better and better telescopes. But all these telescopes, there was, tubes with mirrors and lenses in them, were really just designed to detect optical light, the kind of light that our eyes can see, the kind that with the wavelength in that range that our eyes are designed to see.
Right, so those sorts of telescopes, they would take the visible light that was coming in from out of outer space and kind of just magnify it so that we could see it with the resolution of our eyes, right? It didn't actually show us anything outside of the visible spectrum.
It effectively made our eyes a lot bigger.
Yeah.
Our eyes were better. We had, eagle eye vision or superior to eagles in a lot of cases. But yeah, it was still like using the same kinds of photons to carry that information from, our object out in space to our eyes. But in the middle of the 20th century, astronomers started to do things differently. They started to look at kinds of light that our eyes can't see. So they started to do things like use radio waves as cosmic signals and building telescopes that detect those radio waves. They started to look at infrared and ultraviolet light. They started to use X-rays and even gamma rays as cosmic messengers. So, astronomy went from being a purely optical phenomena or a field of study to a multi-wavelength field that used all kinds of different light. And then even more recently, we've moved beyond light entirely. We still use telescopes to see all these kinds of light, but in addition, we study our universe using detectors that measure things like the ripples in space and time that we call gravitational waves. And we also study the universe by building enormous things we call neutrino telescopes that detect these kind of very elusive, very ghostly, very feebly interacting particles called neutrinos that can travel from some of the most volatile and interesting, dramatic parts of our universe straight to our telescopes where we can study them and hopefully learn about those weird environments.
Right. So it's almost because neutrinos are these incredibly, uninteracting objects that they actually can come to us from places that normal light's not going to make it to us from.
Yeah.
So they let us see things that any kind of normal light would not let us see.
Like a really, easy to understand example is if you want to study the core of the sun, not the surface. Like when we look at the sun, what we're looking at is a picture, an image of the surface of the sun. Mm. But when we use a neutrino detector to look at the sun, we can see these neutrinos that are produced in the sun's core and travel straight out. Like they don't scatter at all as they try to escape the sun, at least at low energies. So these are, kind of direct messengers that tell us about the nuclear physics processes that are going on in the core of that sun. And when we think about other things out in the universe, we can imagine a lot of different environments where the light cannot easily escape, but the neutrinos might be able to, and oftentimes can. And if we can get a good picture of those, we can learn things that light just can't teach us. So on a number of previous episodes of Why This Universe, we talked about neutrinos, these elusive particles. So you can always go back and check out those episodes if you want the refresher on these exotic particles. But in a nutshell, these particles are extremely feebly interacting, extremely light. They travel at almost the speed of light. And, they don't experience the strong force. They don't experience the effects of electromagnetism. So they only interact through the forces of gravity and the weak nuclear force. And this means that, for example, a typical neutrino can travel straight through the Earth without anything happening. It's just an empty background for it. It doesn't experience the solid nature of the Earth that other particles do because of their electric charge. So that also makes them very, very hard to detect. So the first neutrinos were detected back in the 50s. These were neutrinos that were produced in a nuclear reactor. And then in the 1960s, they were detected from the atmosphere when they were produced in the interactions of cosmic rays. And then shortly after, they were detected from the sun in an experiment called the Homestake experiment, which is in a mine in South Dakota. So this was really the first example of neutrino astronomy. We saw neutrinos that were coming from the direction of the sun that were produced in the nuclear reactions that were taking place in the sun's core. And then some time passed, and in 1987A, a big supernova exploded on the outskirts of our own Milky Way galaxy in something called the LMC. This is hard for me to pronounce for some reason, but it's the Large Magellanic Cloud. I can't say it very easily, so I'll try to say it slowly.
Large Magellanic Cloud. There you go.
Thank you. Magellan, that guy. Okay. So this was kind of, again, like not very far from us in cosmological terms or in astronomical terms. It's only 168,000 light years away from Earth. And this makes it the closest supernova that human beings have observed since 1604. So we kind of got lucky that this thing happened, so nearby, so recently. This particular explosion was caused by the rapid collapse of a massive star. That's what it's called, a type 2 supernovae, which is a sort of core collapse supernova. And we call it supernova 1987A for the year and being the first one of that year. A couple hours before the light from the supernova reached us, 3 separate neutrino detectors detected a bunch of events. A total of about 25 neutrinos struck those detectors. And the reason that they saw the neutrinos before the light is because the neutrinos are produced when the collapse happens, and the energy from the core can just like free stream out in straight lines in the form of neutrinos. But the light takes a few hours to kind of bounce around and scatter off of things before it can reach the surface and start to travel away quickly. So neutrinos provide us a kind of a deep insight into that collapse moment itself.
It's like all of the light that was produced in the collapse, it kind of loses some of that initial information that would have taught us about the collapse, because all that light is bouncing around, hitting each other, deflecting. And so it's not coming from exactly where it was produced, whereas the neutrinos are just coming straight at us.
You could think of it as like a giant cosmological telephone game. Every time a collision happens, a little bit of the story you're trying to learn gets diluted, and by the time the light reaches you, it still teaches you something, but it doesn't tell you as much as you'd like. The neutrinos are direct messengers. Mm-hmm. And in this case, the number of neutrinos we saw in their energy tells us things like how hot the core of that star was when it collapsed. And it tells us things like how much of the total supernova's energy went into neutrinos. And it turns out that like 99% of it did. Mm. So for, every 100 joules of energy that this thing released, 99 of those joules were carried away by neutrinos.
Okay, cool. So that was 1987, right? So
that's right.
How does that bring us to where we are this week with the IceCube experiment?
Well, if we had to wait, another 300 or 400 years before we saw another supernova, that would be a very slow way to do astronomy. So what we wanted to do is build bigger and bigger and bigger neutrino telescopes that could see things from farther away. And I would say that there were lots of efforts at this for a while, but like this science didn't really get off the ground until the completion of the neutrino telescope we call IceCube. So IceCube is not your typical telescope. So don't picture something with lenses and mirrors. There aren't any lenses or mirrors that make IceCube work. Instead, it is a giant chunk of Antarctic ice. So like something about a cubic kilometer in extent is instrumented here. It's at the South Pole.
So they're not lying when they called it IceCube.
That's where the name came from. So my PhD advisor back at the University of Wisconsin, Francis Halzen, this was sort of his brainchild. He played a big role in getting this thing off the ground. And he was really excited, I remember one day when he learned that the IceCube Experiment's webpage was getting more hits on the internet than the rapper IceCube's webpage was. That was a big deal for him and for their experiment. We all had a good laugh at that. But yeah, so, okay, let me paint a picture of this incredible telescope. So it's at the South Pole. It consists of 86 strings of detectors. So picture like, kilometer long, so kilometer long strings with little detectors spaced out over those strings. And they're vertical. So to get them into the ice, they use a hot water drill. They make a hole 2.5 kilometers down into the ice and then lower the string of detectors into the liquid water and let the ice freeze over them again.
So there's no box that the detector's in. The detector is literally just like a bunch of detectors scattered throughout the ice. It's like the ice is part of it.
That's right. About 5,000 detectors embedded in the ice. Yeah, with like electrical cables connecting them all to record all their information. Right, exactly. So we've got this cubic kilometer of ice, and the way it sees neutrinos is so most neutrinos travel right through the ice and nothing happens, and you don't see those, you don't detect those. But 1 out of a million or so, when they get in that part of the ice, they scatter off an atom or a nucleus or something in the ice. And that can do a couple of things. Some of the neutrinos, the neutrinos we call muon neutrinos, can produce an energetic particle called a muon. And this thing has charge, and it will plow through the ice and will just put energy off in all directions. And you can measure with all these detectors the trajectory of that muon and kind of reverse engineer where the neutrino must have come from and how much energy it might have had. Other kinds of neutrinos hit again, a piece of nucleus or atom or something and just create a big spherical shower of energy. And again, these detectors can try to do that. And there are even weirder kinds of events that we call double bangs, where a special kind of a neutrino called a tau neutrino that with a lot of energy can produce two separate showers in two different parts of the detector. So this kind of gives you a way to measure this third kind of neutrino. So there are a bunch of different ways you can try to see this, but in each case you get an idea of how much energy the original neutrino had and what direction it was coming from.
Okay, so IceCube's been collecting data since 2010, right? So what have they seen since then?
Well, a few years into their run in 2013, they announced that they had definitively seen astrophysical neutrinos. So these aren't neutrinos being made in the atmosphere or something. These are neutrinos coming from beyond the solar system. These neutrinos had tons of energy. In the kind of units we use, they're anywhere from like tens of tera electron volts, or TeV, which is like more energy than the LHC, Large Hadron Collider, produces, for contrast, all the way up to like PeV, which is, another 30 times higher. So like really, really energetic particles, much higher energy than we can produce in any experiment here on Earth. But we didn't know where they were coming from. We had a bunch of guesses and theories, and I'm a theoretical physicist who works on neutrino astronomy, so I had all my own ideas too about where I thought these neutrinos might come from. But they kind of just pointed from everywhere in the sky. We assume they point at things, but like if you only see one neutrino from each thing, you can't really be sure where they come from. So it was a big mystery, and we all kind of wondered. One thing I thought they might be coming from were these objects called gamma ray bursts. These are like big stars that explode in kind of even bigger fashion than a normal supernova. But it turns out that's not where most of these come from. The neutrinos we see don't point at known gamma ray bursts, and they don't happen at the same time as known gamma ray bursts. So most of these are not coming from gamma ray bursts, I think is pretty clear now. Another thing that a lot of us thought they might come from would be a certain kind of supermassive black hole that's actively accreting matter and producing big jets of energy. And some of those are pointed in our direction. These we call blazars, and we thought maybe these would make the neutrinos IceCube was seeing. But that doesn't look to be the case, at least not most of them. They don't seem to be coming from these blazars. So we really didn't know. And then on Thursday, November 3rd, they had a big announcement. A few dozen of my colleagues at the University of Chicago gathered in our conference room and watched it live. We played a little game called Press Release Bingo, where everybody got a bingo card with words we thought were likely to be used in the press conference. I did not win Press Release Bingo. I'm a very competitive person, so it's hard for me to play a game and not win. But I got over it. I'm no longer hold it against the winners of Press Release Bingo.
But it does go to show, for anyone who doesn't know, that these announcements are kept pretty good secrets until they're out to the public, even to people in the physics community, as long as those people are not part of the IceCube experiment. So anyone out, like even Dan, who works on neutrino astronomy, did not know what this announcement was going to be until the public knew.
Yeah, I was having a bunch of conversations where people were kind of like widely guessing or speculating about what it might be. We knew there was going to be an announcement. And we knew that IceCube was not in the habit of making press releases if there wasn't a pretty big result. So we thought it was going to be something important, but we didn't know what. Pretty much all the guesses were wrong, at least the ones I heard. So what they did tell us is that there's this relatively nearby galaxy called NGC 1068. It's also known as M77 or Messier 677. It's only 47 million light years away, which you can think of this as, it's not your next door neighbor in terms of galaxies, but it's like down the block. It's on your block, but in the other end of your block. It's pretty nearby cosmologically speaking. And this is a really like notable galaxy in the sense that it's really luminous. Okay. It's really bright. Between it being very bright and being nearby, it, has been a target of astronomers for a long time. I think it was seen with a telescope for the first time like in the 1770s or something. So like we've known about this galaxy for a long time. I've never done it personally, but I'm told that if you have a really good pair of binoculars, you could in principle see this object. You don't even need a, fancy telescope. So this is an object that stands out in the sky. And it's also been something that neutrino astronomers have been interested in for a long time. In particular, this isn't just a galaxy. It's a kind of galaxy we call an active galaxy, or a galaxy with an active nucleus. So active galactic nuclei, we call it, or AGN. So this is basically a galaxy that has a supermassive black hole in its core, so millions or maybe billions of solar masses. And that black hole is steadily accreting matter onto it. And as that matter falls in, it gets sped up to nearly the speed of light, where it gets, in a really volatile and dense environment. And everything's very, very hot, and everything's very, very fast and energetic. And that can propel particles and energy out of the AGN, out of the galactic nucleus. And in principle, we think this is the sort of thing that might accelerate particles like protons and nuclei to really high energies. And those particles might smash into stuff like radiation or gas, making neutrinos that a telescope like IceCube could maybe see. So we've got a bunch of good things. We've got a big black hole actively accreting matter in the sort of way that we think might make neutrinos. Also, it's really nearby. It's certainly between those two things, this would be on your short list of targets to but to look at in your data with your IceCube telescope in the hopes of seeing high energy astrophysical neutrinos.
Okay. So I assume they did that. They looked towards that galaxy, towards that active galactic nucleus, and what did they see?
All right, so over their more than a decade of operation, IceCube collected a lot of data in all directions, including in the direction of NGC 1068. And what they reported on Thursday is that they've seen about 70 neutrinos from the direction of that object, 70 more than they would expect from backgrounds, okay? The energy of these neutrinos is in the roughly 1 to 30 tera-electron volt, or TeV range. And you can think of this as being comparable to the sort of energy that particles at the Large Hadron Collider reach, okay? So some are a little more energetic, some are a little less, but in that sort of ballpark. So this is an example of a natural object that is producing particles with comparable amounts of energy to our most spectacular accelerator here on Earth.
Wow, cool.
Yeah, it is. It is very cool.
So up until that point, everyone had guesses that maybe these active galactic nuclei were producing neutrinos. This is now we have the solid evidence from the IceCube experiment that they really do. And we've seen those neutrinos, and we've seen that they're of very high energies, and that they're being formed in the active galactic nucleus.
Yeah, at least one of these things, and if one is doing it, probably lots are. Mm-hmm. And we still don't know, is this kind of source making a lot of the neutrinos that IceCube's seeing, or just part of them? Are they the whole story? Are they a fraction of the story? I don't think we really know the answers to that yet. Mm-hmm. But I tell you, when you detect neutrinos from an object for the first time, that's a pretty exciting moment. So just as a side note, there's another galaxy known as TXS 0506 plus 056 that may have also produced neutrinos that were detected by IceCube. They made that announcement a few years ago. But in my opinion, that data isn't super solid or definitive. Maybe IceCube saw neutrinos from that active galaxy, or maybe they didn't. But for now, I'm treating that as provisional, whereas I'm a lot more convinced that the neutrinos from NGC 1068 have really been detected by IceCube. If I don't say that, somebody is going to complain. So.
Fair.
So I started to hear rumors that IceCube was seeing neutrinos from NGC 1068 a few years ago at conferences and things. I remember kind of looking into it at the time and seeing, do I think this makes sense? What could we learn from this, and questions like that. And I had some conversations with people. There's a former grad student of mine, Carlos Blanco, and I had some conversations about these few years ago. And we kind of thought it was unlikely that NGC 1068 could be making this many neutrinos. And the reason is because, as far as we know, the only way you can make high energy neutrinos also causes you to make high energy gamma rays kind of, side by side. You can't really make many more neutrinos than you make gamma rays. But, that we have gamma ray telescopes that point at this thing, and we didn't see very many gamma rays from the direction of NGC 1068. So we kind of discarded this possibility back at the time. Now I'm starting to think that might be a mistake, because NGC 1068 is kind of a special environment. One where maybe you could have absorbed all those gamma rays while allowing the neutrinos to get out. In particular, if you go really, really close to the black hole. So right in the environment immediately surrounding the supermassive black hole in the heart of this galaxy, this whole region is chock full, like densely packed with gas and dust and radiation. So if the neutrinos are almost entirely being produced right there, right next to the black hole, the gamma rays that get produced alongside those neutrinos might never make it out. And that could be a self-consistent picture. I think that's probably the likely story at this time. But I think there are tons of questions we don't have answers to yet. And a lot of people are going to be working on this in the days, weeks, months, and years ahead. So right now, the bottom line as I see it is that we've never seen anything like this before. And that is just fundamentally exciting. Anytime you have a telescope that sees something that's never been seen before, 1,000 physicists go to their chalkboards and start to think. And that's really, it's fun to be a scientist in those moments.
Right. And to be clear, what we've never seen before is high energy neutrinos made from an active galactic center. Right?
That's right. Or even just any high energy neutrinos that point at something that we can identify.
Okay.
This is the first source of high energy neutrinos we've ever been able to identify. It happens to be an active galactic nucleus, but, but we never see anything else either. So this is pretty cool.
Okay, so this is almost like the first time neutrinos can be used as a telescope, right? Like to see an object in space that otherwise we can't see.
At least at these energies. We saw the 1987A neutrinos, but those were a lot lower energy. These are a fundamentally different animal. This teaches us different things than that does. But as exciting as all this is, I think at this moment, the observation doesn't give us very many answers. It just raises a bunch of new questions. My hope, and I think my reasonable expectation, is that this information combined with other information from other telescopes is going to give us important insights into the environments that surround active black holes. It could also teach us things about how protons and nuclei are accelerated in astrophysical environments to high energies. In other words, how cosmic rays are created. Might even tell us something about where the cosmic rays we observe here on Earth come from, which is still a mystery. By combining this result from IceCube with information from other kinds of telescopes, I suspect we can get a more complete picture over time and eventually fill in enough pieces of this puzzle that we start to see a coherent picture. And I also suspect that as time goes on, IceCube and other neutrino telescopes will eventually and gradually discover more sources of high energy neutrinos, allowing us to finally figure out where these mysterious particles come from, how they're created in our universe, and what they tell us about these extremely rich and volatile corners of our cosmic landscape.
Why This Universe is brought to you by the University of Chicago Podcast Network. It's edited and produced by me, Shalma Wegsman, and my co-host is Dan Hooper, a professor of astrophysics at the University of Chicago and Fermilab. If you like our show and you want to support us even more, you can find us on Patreon. There you can access ad-free episodes of the show, as well as exclusive Ask Us Anything episodes where you get to ask Dan and I direct questions about physics or anything else. So if you are curious about that, you can find it at patreon.com/whythisuniverse. Thank you so much for listening and for your support.
Magellanic cloud. I'm saying it wrong. Can you say it?
Large Magellanic cloud? Is that
like Magellan? Large Magellanic. Magellanic.
Large Magellanic cloud. Large Magellanic cloud.